Perfect. Okay. Let me just present you. So Brian Plummer is an assistant professor in the Department of Computer Science at Boston University. And he obtained his PhD in the computer vision group at the University of Illinois. And his research includes significant work on vision language understanding, including applications in phrase grounding, vision language navigation, detecting manipulated media, and disentangled and structured representation learning. His work spans machine learning, computer vision, natural language processing, with a focus on approaches to develop tools for assistive technology applications, including human-AI collaboration and building interpretable and unbiased models. So Brian, we are really happy to have you here. Can you put the slides in presentation modality?
Are they not? They should.
Can you do it again? Because it seems that we can see the slide, the next one, and the comments you made in the slide.
Let me see. You know what? Let me try this a different way. Really quick. Is that coming out better?
Yes. Can you just go just one slide just to check that everything is fine? Okay. Okay. That's perfect. Thank you, Brian.
Great.
You can
Thanks.
start.
All right. Let me go ahead and back. Sorry. All right, so thanks for having me, everyone. So I'm going to go ahead and get right into it. So today I'm going to be talking about this problem of detecting neural fake news, and this is kind of joint work at BU done with one of my PhD students, Ruben Tan, as well as another professor at BU, Kate Sanko. And so towards the end of the talk, I'm also going to talk about some of the ongoing work and just touch briefly on that where we're going at BU. So kind of unfortunately, we have to kind of begin with this by defining what neural fake news is. Unfortunately, a lot of the term fake news has been overloaded. So it has many different definitions in different contexts. So here, when we talk about neural fake news, what I mean is that it's going to be news that is generated by a machine. Right, and so in our setting, the machine is given a title, and then we must generate a news article from it. So you could ask it to generate any of the other components, like the captions for any of the images, or to provide a plausible author's name, or any of these kind of other kind of metadata information. But in general here, more or less what we're just talking about is that at least some component of this article is going to be generated using machines. And so, a lot of the language models have been getting quite large, and because of that, they've been kind of adding all this capacity that has enabled them to take advantage of a lot of this web scale data. And this means that a lot of the semantics and information about the world and kind of language in general kind of gets baked into them, and they're getting more and more accurate all the time. And as a result, these generators are actually getting quite good at mimicking human language for a wide variety of settings. And just to kind of illustrate this point, I wanted to give a quick example, which it was a study I think was done at UC Berkeley, which basically what they did is they recruited a bunch of college professors and had them grade essays. And these essays were kind of on a range of topics. But one thing that the professors didn't know was that these essays were generated by GPT-3. And kind of surprisingly, these language generators did much better than you might have expected. They even got up to like a B- on a history essay for American exceptionalism, as well as a policy memo for a law class. So this was, both surprising and a little bit worrying that these models are getting well enough that they could get, at least for undergrads, a passing grade. So that's a bit of a worrying concern here. So, for this, one of the works that we were kind of most focused on here, because we're talking about news articles, was this work from Ye-Chin Choi's group out of University of Washington. And here what they did is they took essentially the GPT-2 generator of language models, and they trained it specifically to generate articles. And they trained it in such a way that it could also generate any of the kind of other metadata that came along with this, right? So you could end up having it, generate the title or the article itself, or, maybe even the author's name, right? So this is, being able to generate kind of all these components means that they would be able to generate essentially anything you'd want to for a kind of news article. And so what we started looking at here was like, well, or at least one of the things that we found or from this work, oh man, it's stuck. There we go. Is that given a headline, and this headline, can be something like, like link between vaccines and autism, Grover can now generate essentially the rest of the article. And this, saves a considerable amount of time for any bad actor who wants to take advantage of any of these kinds of systems. And kind of one of the things that I found most alarming when I actually read this paper was that humans found that their misinformation that was generated by Grover was actually more trustworthy than something that was written by a human. And you should kind of let that sink in when you think about these, and kind of to me it like gets into a bit of a, like I said, worrying about this, because that has a lot of implications, especially as we look out over the next few years when these things are just going to get better and better as we need to kind of battle this kind of misinformation. So when we started looking at this problem, what we'd seen kind of up till this point was that, actually, let me grab this quickly. That essentially, so far, the neural news story was only considering text. So they were only getting into the text of it, not necessarily the images. And that's kind of a big deal, because it's been kind of shown that in kind of news articles and like social media posts, if you actually have images in them, they're going to be much more engaging and it's going to reach more people. So we'd assume that most of the bad actors are more than likely going to be incorporating text or be incorporating images along with their text, just so it reaches more people. Now, when we start thinking about, okay, what do these kind of images mean? One of the things that you could do is you could start trying to also generate these images, right? So you could use one of these kind of GAN methods to generate images, based on whatever kind of article that you were looking for. But when we kind of look at a lot of literature, what we've seen is that fake images are detectable, at least for now. In this kind of work out of UC Berkeley, they kind of separated everything, all the images out for some of the recent methods, like recent GAN generation methods, and started separating them out into how difficult they were to detect. And when I sit there and I look at this kind of manually, even some of these ones in the 25th percentile, they seem relatively easy for me to identify. So for this, when we were actually considering our threat model, we decided to try to avoid this question of using GAN generated images, because like I said, right now we can actually detect them pretty well. So when we were building our threat model, what we assumed is that the images are manually selected, right? So, if I'm trying to find, if I basically have this article about Obama and this kind of health care bill, I can, just spend a couple minutes, go and find an image of Obama and just slap it in there. Now, in this particular example, while the kind of text we have here is generated, and the photo is a real photo, although it might not have come from this context, so it might have just been pulled from the web. The caption itself is also manually generated, but we also considered scenarios where the caption was generated as well. So this one may or may not be real. In this particular example, it was a real caption that was human generated, but it need not necessarily be. So when we think about, okay, so now we kind of have identified what our landscape is, and we think about what kind of weaknesses in these language models can we take advantage of, that it would either be impossible or at least really, really hard for them to avoid, so that we can hopefully be able to detect these kinds of neural news images. And so the one I'm going to kind of reference the most, is because it's the one that we looked at quite closely, was looking at consistency between the media, right? So in our case, we were looking mostly at the text, whether that was article text or the captions, and how well that they matched the images. But of course, this could come up in other settings, for example, with the audio, how well the audio matches the video. So the whole idea here is more or less to just try to find these kind of inconsistencies between these two different modalities. But of course, there are several other methods or other weaknesses that we could exploit that we weren't in this case. One of them is, of course, a lot of these GAN generators have challenges generating very complex scenes. Or if it's a video, they could be looking at what the style of a person is, their kind of mannerisms, things like that, to try to look for inconsistencies if it's like a well-known person and they can exploit this kind of information. Or if there's some kind of factual inconsistency, right? So it's about some well-known topic or something we can have a trusted source from, and we notice that there's some inconsistencies between these two. So like I said, our main focus here is, at least in our work, was looking and trying to ensure that there was kind of consistency across the different modalities. So now we're going to kind of get into at least how we try to exploit these inconsistencies to help to defend against some of these neural news articles. So kind of at a high level, what our model does is to compare the article and any images associated and the image captions. So our goal is to kind of check for inconsistencies between these different modalities, right? So a good example is to say, ask whether or not the text itself was consistent with the photo. But this could also be, if the caption itself was consistent with the article. And one of the things that when we started looking at this problem that we noticed was that in many of the kind of generated articles, even when they were generated with a image, let's say it had a captioning model that specifically was trying to ensure that there was consistency between the named entities in the caption and the articles, that kind of despite this, there was a decent number where there was actually different named entities. And this, of course, did occur a little bit more when we were actually using human generated captions and we're generating the articles themselves. So, just, kind of with the current models, we're not able to ensure that these entities, at least off the shelf, weren't able to ensure that these entities remain the same between the articles and the captions. And so this actually came a pretty strong indicator of whether or not something was fake or not. So it was, of course, one of the things we needed to take advantage of in our model. All right, so to just kind of summarize the contributions of at least this particular paper, this work was the first to address basically both the visual and the linguistic aspects, at least the best of our knowledge, of to be able to detect neural fake news. We also used Grover to create a data set based off of good news. And so we call this the neural news data set. And this, basically contained a mix of, of course, real articles from the good news data set, as well as essentially some machine generated one. And we didn't just, carry out an empirical evaluation of our model. We also spent a decent amount of time, trying to understand what humans thought of these articles, and also, which components were really important. So we had, that to help try to identify any of these kind of weaknesses, and it also helped us train our users a little bit more. And kind of finally, we introduced this kind of named entity-based model, and we found this a pretty good baseline for automatically detecting neural fake news. All right, so to get into some of the details of what this data set looks like, so like I said before, we actually expanded on the good news data. So we had 4 types of articles, and the first type was essentially just the good news articles as they were. So these are essentially our pristine articles. They have like no modifications. So they have the real articles, real captions, and, as well as the real images, because like I said, we were only using real images, and we weren't actually generating any of them. And so then what we did is we took these articles, took their titles, and then used Grover to generate an article, and used the image captioning method that was designed for the news domain to caption the images. So we ended up setting, getting these set of articles where, we still have, like I said, a real image, but the article text and the captions themselves have been replaced with machine-generated ones. And the other 2 types of articles that we were looking at were just doing a mix and match of these real and generated articles that we had, just to sit there and try to understand, which one was most important, and how focusing on one or the other one might change, humans' perceptions of our systems. All right, so before we get into the kind of model, I'm going to give at least a taste of at least some, one of the human evaluations we did on our data set. And so the first thing that we did here is we asked the users for a set of things like, can you rate their article on style or content, as well as explicitly ask them to, match the consistency between the images and the articles and captions, and then also, finally getting into an overall like trustworthiness to, do they trust this article? And kind of one of the, disappointing things is that there wasn't actually much change. When I look at this at a high level, there might be some slight changes between, one type versus the other type. And here, just to point out, we were testing all 4 news article types. So this is, first to have the real articles in them, and the last 2, of course, the articles have been replaced. But despite this kind of mix match, the humans didn't, necessarily rate one necessarily much better than the other. So this is a bit troubling. But one thing that we did do is we also had some other user studies in our paper to actually try to train our users to better detect neural news, and we did actually have some success with that, mostly dealing with the named entity inconsistencies, and we try to get them to explicitly pay more attention to the consistency between the captions and the images in the articles. And so they did get a little bit better, but still they're, weren't, they weren't that good at being able to detect them. So it's still, much worse off than we'd like it to be. But if you do have any kind of interest in this kind of stuff, you can look at our paper on the topic. All right, so when it comes to training a model to detect neural news, a lot of the prior work, like in Grover, what they would do is they would take, let's say, their language generator or GAN generator, and then train a model using either real and generated articles, and they would use, and then they would test to see this on like unseen data, just to see if it could pick up on any of the fake news in that regard. But the assumption that you actually have a generator was a very strong one that we didn't really want to be restricted by in our work. So, and this is because, defending against manipulated media, it's always a cat and mouse game, just like security is, where we can't assume that we actually know what the generator is, because the adversary might be kind of using any generator they want, might even be using custom ones, so it might not even be a publicly available system. So we wanted to at least avoid having to use kind of any kind of language generator. And so this, of course, means that we have a lot more limited training data, because essentially all we have are examples of real articles out there in the world. So what we end up having this idea is, like, if we know that the model has trouble getting consistency between the images and the captions and the articles, we can explicitly train our model using the pristine articles by essentially just mismatching the articles with other real images. And to give an illustration of exactly what that looks like, this is the kind of example we had before. We're here on the left, we have a positive pair, so this is going to be essentially the ground truth, like pristine article. So this is our type A articles. And then we would just pull some other image from some other article, and we'd match it to the article here on the left. And they, of course, should be, have some kind of semantic inconsistency between them. It might be a little bit greater than it would be for an article that was actually, for a, Grover generated article, that might be a little bit closer, but this at least gives us an idea of, trying to capture this kind of information between the different modalities. And so kind of with this augmented training set, our goal was then to determine if a news article was generated or not. And so what we ended up doing is we first started out by using kind of a bottom-up approach. We took all of our images in the news article, and we got basically the bottom-up object representations that's often been used in a lot of vision language tasks. And this gave us essentially a set of vectors, which are essentially just the region boxes for the images in our article. And then we took the caption and our article, and we encoded them using BERT. And then for the captions, we took all their word representations, and we compared them to our object representations. And we ended up basically building this object by word interaction matrix that helped us to measure essentially how consistent the two were with each other. So, are there words that are kind of matching some of the kind of visual elements that we're seeing in the images? And then what we did is we took the article representations, and we would compare this kind of object by word interactions with our object article representations to get an overall like visual semantic feature representation out of it. And of course, as we said before, we did identify that if there were kind of any inconsistencies between the named entities, that this was a strong signal. So we just included this as a binary feature that we concatenated onto the end of our feature vector. And then once we got this visual semantic representation, we just passed it through a very shallow detector, just consisting of a couple fully connected layers of batch norms and ReLUs. And the output of this was just a single number probability that the article is machine or user generated. With this method, we ended up, being able to get 64% performance. In this case, we had even numbers of matched and mismatched articles, real and generated articles. So random chance would have been 50%, right? So just using a simple method like CCA, we get 52, so just barely higher than random. But using both this trained mismatch as well as our named entity indicator, we were able to get much better performance. Despite that, we're still very far away from where we'd like to be. And so, one of the things we did, see from prior work is that if we did include some generated articles, we would get better performance. So we also, included some of this information in our training procedure. And that, of course, kind of confirmed with prior work that you could do much better. One thing to point out here is that the test set was Grover mega articles. So this first column here, for all the ones that are including these generated articles, this is in the kind of best performance, best case scenario. If you actually know what your your adversary's generator is, this is how well you can do. And we notice here that we're getting we're still doing pretty well, but we get a decent dip in performance when we're using a different generator. And so this kind of helps us to simulate how these might be used in practice, where you start out with your current generator, you do the best you can, but at test time you're going to be seeing some kind of unknown generators from our adversaries. So what we actually ended up wanting to do then is from here, we're like, well, we'd really like to be able to bridge the gap between seen and unseen generators. And so what we had imagined here in some of our kind of ongoing work is we're thinking about what the feature representations for these two generators might look like. And what you could imagine is that let's say you trained your generator, but there's some website that you're pretty sure has some machine generated news on it. So then you go through, you scrape that website, and you don't know which ones are machine generated, which ones are human generated. So it's essentially just some unlabeled data. But what you'd like to be able to do is essentially align them. And this, of course, is the exact kind of scenario that comes up in domain adaptation, where you basically have your training data and our source data in this case would be Grover large articles. And there are going to be some Grover mega articles mixed in with some real articles that we just don't have labels for. And our goal here is just to be able to align these two feature distributions. So hopefully they'd be able to generalize better. And the nice thing is that kind of off the shelf, we actually did see this kind of boost in performance just by taking like a recent domain adaptation approach and combining it with our DDAN model. We were able to get half of the gap between these two closed down. So just really straightforward approach. We're already getting a decent amount of gain. Now, one of the kind of worst case scenarios for us to think about with this kind of cross-modal inconsistency issue is that Grover itself was blind to images and captions. It was never trained with any of this information, so it was never trained to actually try to make these consistent. So one of the worst case scenarios that could happen is if all of a sudden you made Grover see these captions and see these images. So we started trying to integrate this kind of information into our training process. And while let's say providing some human-generated captions might increase the amount of work that you have to do, what we found was that with that kind of small additional efforts, the news articles become much harder to detect. Now, in this case, I will point out that the DDAN model we're using was trained with this binary named indicator variable. Maybe if the consistency is going to be stronger now, maybe that's not going to hold up anymore. So this is still like very preliminary work, but it was also a bit troubling that we saw such a drop in performance with this just relatively small change. So we're kind of coming up on time, so I'm gonna just briefly go over probably this first one. So one of the things that we're worried about is that, so far, we're talking about where things are currently, and the single modality deepfakes themselves are getting better, and they're getting more and more difficult to detect. So this was an example where basically someone generated, text, photo, captions, kind of the whole deal of claiming that Obama was going to be in the next Black Panther film. And this was a bit more accurate and a bit more convincing than we would like it to be, because it still sounded like him and everything. So it's already worrying where things are going, and we can just expect these to get worse over time. Our hope is that the consistency will still remain, but that's not entirely clear. And kind of with that, I'll ask if there are any questions.
Brian, thank you very much for your presentation. So let's see if there are some questions from the audience. In the meantime, Mike, and I would like to, I have actually a curiosity about what you've said with the building of the creation of the data sets, where you also create the caption to the images. I mean, how is the process to do that? I mean, do you have a sort of image to text when you generate the caption for the images, or is it something completely different? I mean, not the human captions, but the one that are synthetic.
Yeah, so basically we used the image captioning method that came with it was introduced with the Good News data set, and essentially what they did is they took the title and the article of the image, or article of the news article, and as well as the images input. So essentially all three of them were given as input into their captioning model. And what they would do is they would generate a caption. Any named entities were just given a special token. And then the named entities themselves were basically inserted into those tokens based off of what was in the text.
Okay, great. I mean, so also the text of the article was used to generate the caption. Yep. So they were quite realistic. Okay, and it's very interesting that now you're also working on images and I mean all together. And you're right that probably it's not easy to keep this consistency across different modalities. So that's really interesting.
Hi, I have a question.
Hi, Alex.
Yes, I had a question about the user study that you did. I know that from my experience, asking people to do anything that's not completely easy, it can present challenges in extracting the information. So, for example, what was the expertise of the users? Were they native speakers, for example, or not? Was there some sort of consistency, consensus rating for the answers, etc.? Could you just tell me a bit more about that?
Yeah, sure. So for the most part, we didn't force them to be native English speakers. There was a test to basically rate their knowledge that they had to end up having to pass. But as long as they could pass that test, they were able to do our user study. So there could be some questions about whether, you know, if a native English speaker would have as many of the same difficulties as a non-native speaker, but we felt like this was a pretty good place to start with because, you know, if a news article is written in English, it's not just the native speakers that are going to be looking at it, it's going to be the non-native speakers. So it is a bit more reflective of the kind of use in general. In terms of a lot of the statistics, they were kind of aggregated. So it's not like we, let's say use majority voting to determine a label of real or fake. We just aggregated them all together. Yeah.
Thank you, Brian. Thank you again. And okay, so now we can stop the registration, and we have a